to my talk on domain-driven API-first platforms in bioinformatics. Today, I'll share my journey leading a major platform evolution that transformed our platform to be API-first and helped our company and our teams scale new feature development costs and velocity to be sustainable. Along the way, we also had some great learnings applying concepts from domain-driven design that I'll share and how impactful they were. But before we dive in, let me introduce myself and set up the context. Hi, I'm Ajay Subramanian, Director of Engineering at Generate Biomedicines. At Generate, our mission is to program biology to transform how medicines are created, developed, and accessed. The way we do that is by instantly generating optimal therapeutics for the greatest impact on human health. Our scientists use our Chroma AI model to design proteins that have specific therapeutic properties. We then evaluate those proteins in our wet lab for their pharmacological properties and parameters. We capture the experimental data digitally in our data platform to further use for refining our AI model training, as well as for the more promising candidates. We do have clinical trials. We put them through clinical trials. We have a strong pipeline that continues to get better and better. So with this design, build, test, learn loop, we hope to go from drug discovery to drug design. A little bit about myself before Generate. Prior to Generate, I led the data interfaces group at Benchling, where much of this work is informed. Before Benchling, I led LinkedIn Learning for Enterprises, from launch through various stages of growth over 5 years. If you're interested in learning more, please do connect with me on LinkedIn. And over the next 20 minutes, I want to take you through this journey that I just mentioned of taking a platform that was approaching gridlock and imminent failure to one that became a strong foundation for growth for the company and for the customers. So first, we will set some context on the world as we found it. Then I will walk through the 3 major architectural decisions that turned things around. Finally, we'll talk about looking back at the before and after world and how that changed the real impact that it created, right? Awesome. So a little bit about Benchling. Benchling is a cloud-based scientific research and development platform. It is designed to help biotechs and their scientists accelerate the pace of modern science by firstly modeling and automating their scientific data and workflows, and secondly, helping them digitize their scientific collaboration and lab operations. The main capabilities that help them do that is molecular design, lab notebook that helps scientists design molecules and collaborate with each other, experimental data capture and analysis, and finally, end-to-end workflow automation. So let's build on the context a bit. When I started in the platform organization, we were serving over 200,000 scientists on the platform. Data volume was roughly doubling every 7 months or so. And the diversity of data was also growing due to the novel scientific experiments that our customers were doing. Just to give you a sense of scale and diversity, we had over 100 platform native types, over 5,000 customer-defined types, and over 40,000 categorical types to tag and analyze the data. This should give you a sense for how much the customers extend the platform to model their science as well. Next up, bioinformatics in general has a Tower of Babel problem. What does that mean? We have scientists on one hand who speak the language of biology and pharmacology. Engineers have to understand and map that experimental design and scientific domain language into the language of code and data. in order to digitize the science. And finally, we have analysts who are the business stakeholders who need to make strategic decisions based on how their programs are doing and their experimental programs, when there are key decisions to be made. They speak the language of BI. So, needless to say, a lot of effort goes into understanding the science, modeling and mapping it to a digital platform, and then building and extending the analysis capabilities to, serve diverse stakeholders. This translation costs can be substantial, on the order of months, leading to, building something in requirements gathering, in understanding the science, and also iteration after building something to make sure we got it right. Finally, let's talk about the platform world where we lived, which is at the center of all of these, flywheels around it. We had a platform where each entity had to be plumbed once per vertical product surface, which resulted in an OFN cost of development and support. This led to a fragmented experience for the customers where bioentity coverage and consistency gaps meant missing core functionality in the public API that really hindered our customers' ability to automate their scientific workflows. Also, the 5,000 customer defined types, if you remember, those were treated as second-class citizens in the platform. Finally, this bioinformatics being highly regulated, expansion to new customer segments also meant new regulatory frameworks that we had to comply with. So we had to build platform frameworks that were required, by entities, who support those customer use cases. And this was also increasing the cost and reducing the velocity of new entity development. We call this the platform tax spiral. The net effect here was that the platform was headed towards a complete gridlock over the next couple of years, where it would be near impossible to ship new functionality in a viable timeline before either customers switch to a more specialized competing solution or, even worse, built solutions around the platform in-house themselves. So let's take a look at a little bit more deeply how these show up in the platform, right? Platform had evolved over several years into 4 distinct product silos. This meant that adding a new entity to the platform meant it had to be implemented separately for each vertical, from the database layer to the presentation layer, right? What this specifically meant is an engineer or an engineering team had to write new entity code in 14 different places in the platform. So this is essentially our OFN cost per vertical, which also led to inconsistent coverage, our first 2 problems, which were the major rate limiters here, right? We also had a model proliferation problem, which is the third problem that you see, where the model layer is fragmented, and each vertical had its own technical domain-specific model layer, which came up at different points in time as that silo was being built out. This resulted in inconsistent semantics for the models, poor developer experiences, and also inconsistent coverage and behaviors across the product surfaces for the same entity. Finally, our fourth problem of platform tax, which we just talked about. In each silo, the entity team had to implement the platform frameworks that applied to that entity and that silo, right? For example, public API authentication mechanisms would be different from the web UI authentication mechanisms, right? And the number of such frameworks was only growing, and there was no governance or standards. This was our, platform tax problem. So these 4 interconnected problems were our primary rate limiters that were driving the platform towards gridlock. And there was growth that was going to drive more and more, development along each of these dimensions, making it worse. Next, let us see how we addressed these rate limiters systematically over the three architectural decisions that we made. Our first architectural step directly addressed the first three problems of the OFN cost per vertical, inconsistent coverage, and model proliferation. So we decided to go from this world to this world, right? What this specifically means is API first through dependency inversion around a single source of truth model layer. That's quite a mouthful, so let me break that down. For firstly, the single source of truth model layer, we replaced multiple engineering domain specific model layers with a single model layer. This would serve as the source of truth for all entities in the platform. All higher layer views would be derived from this model layer. As you can see, the client generators generate the client views. Below the model layer, the basic CRUD operations for each model would be, uh, implemented once in a standardized way. Consolidating the model layer in this way also enabled us to achieve economies of standardization and scale, where we could invest in governance and tooling to improve the developer experience and also, scale that across the entire platform entities, right? Indeed, our investment in generating clients from this model layer was a key investment that we made in tooling here, right? We'll talk about that in a bit. Next up, dependency inversion. This is a very important architectural concept. It is the D in solid. It's a powerful principle that says high-level modules should not depend directly on low-level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. These powerful concepts result in decoupling the upper layers, which are policy and presentation, from the lower layers, which are mechanism and utility, and enable them to scale independently of each other. So this is exactly what we did by implementing client generators, and we could actually, solve the OFN problem in an instant. Let's look at that, right? In the new world, the cost of adding a bio entity to the platform with this first step was cut by 2/3. A developer now implements the model layer and below, and we get all the vertical clients for free and instantly. O of n goes to O of 1, and there are no more coverage and consistency gaps. Indeed, the cost for building a new bio entity went from over 6 months to under 2 months. This was huge. With this step, we had solved the first three problems of O of n vertical cost per entity, inconsistent coverage, and model proliferation. However, we had not solved the platform tax problem at this stage yet. So we'll discuss that in the third step. But first, it's helpful and important to talk about key decisions we made at the model layer itself. So what went in there is what we'll talk about next. Great. So our second architectural decision was a combination of three very important decisions we made in the model layer, how we are going to, represent entities in this layer. First thing we did was borrow some concepts from domain-driven design. Domain-driven design is a powerful set of architectural patterns that shines in systems where the business domain models, workflows, and processes are very complex and very central to the value of the software we are using to digitize it. This is the case in bioinformatics, where we saw there are so many different domains, scientific domains even, and we had a huge Tower of Babel problem. So ubiquitous language was the first concept that bridges us across this divide. Instead of constantly translating between the language of science, the language of tech, and the language of analysis, we decided to bring our modeling language closer to the scientific business domain. We made our type system scientifically aware that allowed scientists, engineers, and PMs to communicate precisely about their science and how they map to the platform, right? And the relationships with other entities. Um, the impact was huge. We dramatically reduced miscommunication and translation gaps. And that always helps because the biggest problem in operating in this kind of an environment is that we're talking about different things. Second was bounded context. Bounded context formally define the domain boundaries within which specific terminology applies. Now, bioinformatics spans multiple specialized subdomains, molecular biology, lab operations, data analytics, each with its own very specialized terminology. And the lack of domain boundaries, can be very problematic and cause confusion. So bounded contexts help us eliminate the ambiguity that comes with unclear domain boundaries and unclear semantics within the domains for terminology. So this created modularity and clarity in our model layer. Next up, we decided to go spec first with GraphQL SDL as our DSL for our modeling language. We also extended the tooling to introduce stability notations like alpha, beta, and stable. So when a new entity enters development, it is alpha and only available in the lower environments. When we are ready to test with customers, we promote it to beta, and then customers who are in the beta are able to use those entities. And then once we are ready to support an entity longer term, and generally to all customers, we promote it to stable. So these are basic, what you call hygiene for maintaining public standards and interfaces. Finally, and perhaps most importantly, we addressed our handling of custom types. Understanding that customers extend the platform heavily, this was an important decision for us. We allowed customers to extend the platform provided types, and also with dynamic graph generation, we were able to create a customer specific view of the domain graph, which gave them a specialized graph for their organization. And also their entities, they could see as first class entities in the platform because of the upper layers being views on the model layer, right? This was really huge. This really was another major pain point for the customers that gets solved by this architecture, right? Next, let's talk about the platform tax problem, which I promised we'll come to. I won't go into the details of the context, but I'll summarize that the problems we were looking to solve here were, one, there was no clear definition of what compliant meant for the new features that we were building. There was no central repository for all the frameworks and what are required frameworks in a given context. We were also adding more frameworks as we were entering new customer verticals, and that was also increasing the cost of compliance in this kind of environment. So our solution was a combination of technical, process, and execution strategies. From a technical perspective, we applied the same dependency inversion principle, this time at the ORM layer. We introduced a platform framework interface, which essentially is a framework for frameworks, which decoupled the platform framework providers from the platform framework consumers, who are the entity developers, and across a clean interface, a formal interface, right? From a process perspective, we put in place a definition of done governance structure, which established and formally published all the required frameworks for compliance. This had executive endorsement also. And from an execution strategy perspective, we took a stop the bleeding approach, which essentially meant all new entities and frameworks would be built in the new way. And the existing entities and frameworks would be migrated over to the new world based on priorities. So this was a pragmatic approach to, scale, like address the scaling bottleneck in our ORM layer. Great. So let's take a look at the transformation that we were able to accomplish. This picture shows you the before and the after worlds, and you can read the slide, but I wanted to voice over what this really meant for us, right? We took a platform that was facing gridlock and created a foundation for sustainable growth. The results were huge for our customers who are scientists. What was once a frustrating experience with inconsistent coverage and behaviors in the platform, we now had a cohesive ecosystem where their own custom types were also first-class citizens. For the engineers building new capabilities, their cost of development and the friction was cut down massively. They were more productive. And for the business, it was a win-win because when our customers win, when our employees are more productive, the costs of developing, delivering, and supporting new entities went up went down, and our agility as a platform went up rapidly. The unexpected dividends continued to appear. We had to add a new dataset API as a new vertical in the platform, which was one of the first use cases on top of the new platform. And towards the end of the release cycle, a new use case called mobile backend for front end came up. One of the customers needed a mobile client, and it was unclear what kinds of coverage they might need. We looked into the dataset API, and we were able to leverage the GraphQL layer inside to just infra clone and serve the mobile backend for front end. So in effect, we got the mobile backend for front end for free or nearly free. And this is a really cool example of when your platform transformation, your architecture, supports new use cases which you are not explicitly designed for. And that means that your platform transformation was successful and your design is durable, right? So that's my talk. Thank you for your time, and appreciate you listening to my talk.